Hi guys, my name is Manish Kumar and today we will create system design of nearby friend service. So let's start with step 1 and step 1 is functional requirements. User should get notified if a friend is within 5 mile radius. If a friend becomes within 5 mile of radius, the user should get notified that there is a friend nearby you. User should be able to add, update, remove friends. So user can say like, okay, this is one more friend I want to be notified. I want to get notified if he or she comes within 5 mile radius. So out of scope, we will keep like 5 mile radius distance fixed. So I think from this system design point of view, these are pretty reasonable requirement for this application. So now let's go to step 2, and our step 2 is the non-functional requirements, NFRs. First is system should be highly scalable. System should be highly available and should be consistent, and definitely low latency will be here the key. So I think these are pretty reasonable NFRs for this. So now let's talk about capacity method, that is our step 3. In the capacity math, let's make certain assumptions which is needed for this design. So let's say we have 200 million daily active users, and out of them let's say 10% of users are concurrent user, and each user let's say 100 friends, 100 average number of friends per user. And let's make one more assumption that client app is sending a location update within 25 seconds. Location updates coming in 25 seconds. So every 25 seconds the user, it's the client application installed on the user mobile is like sending location updates to the server. To find how many queries per second, how many location updates per second coming, so it will be 10% of 200 million is like 20 million users having 100 friends and notifying 100 friends in every 25 seconds. So divide by 25, that will come to be query per second. So this will be 80 million location updates. So here we have 80 million location updates coming every second. So let's see what kind of server we need here. So if we see the data size of location update, let's call location updates data size. So it will be what it will have. It will have the ID, user ID, lat, long, and timestamp. So each field here is like 8 byte, which is like 8 into 4 equal 32 byte. So each location update size is 32 byte, and there are 80 million location updates happening. So total size of information or data flowing per second over network, let's call it total size of location updates, will be 80 million into 32 bytes. Perfect. So 80 into million is 10 raised to power 6 and 32 byte. So 10 raised to power 3 byte is equal to 1 KB, 6 byte is equal to 1 MB. So it will be equal to 80 into 32 MB, and which will come out to be 2560 MB. and in short it is just 2.5 GB data. So we have 2.5 GB data flowing over network per second. So it's not a huge. If let's say we have a server capacity is 10 Gbps. Here B is bits, not bytes, keep in mind. So it is approx 1.25 gigabytes per second, GB per seconds. So approx 2 servers can support it, and safer side maybe 3. So here you see the memory, the data size is not a big problem. It's a very small data information flowing. The problem here is the number of request processing per second is pretty high, 80 million. So if we have a Redis server, so Redis server can support up to 4 million. So to be safer side, let's call 2 million requests per second is the capacity of Redis server. So we need 40 servers, 40 Redis nodes. And if it is Kafka, if we say like if we want to use Kafka is like I think it is 1 million. Kafka is like it's a cluster, so per server it is little low, its capacity. So let's assume it's 1 million requests per second. So we need approx 80 Kafka servers to handle this load. So basically the problem is not the data here in this case. That is very important point coming out after this calculation. Data is very small. If it will be only data thing, then only 2 server can support it. The problem is the number of requests need to be processed is huge. And so how it will work, like the request, like a location update will come to the server, it will published or like sent to all the friends, and it's done. I don't see any use case here where we need to store information for longer run or things like that. So I think Redis will be a best option for us. Kafka is good when we want to store things for longer and take them out based on conditions. Here is like simply just like request coming, send it to all friends and good to go, drop the request. So Redis will be preferable option here. So we will choose Redis, but again, as I said, Kafka is not something holding us to do. So if you guys like have better understanding of Kafka, you can go there for that also. That's perfectly fine, I think. Now let's talk a little bit about the database. What kind of database we are dealing here? So in the database, there will be an information table, a user table, which will be having the ID, name, address, contact info. What else? I think the profile info. So if I say 8-byte ID and I say 30-byte name and 100-byte address, contact info 30-byte, profile info maybe 30-byte. So this will somewhere come out to be 198 bytes. So it's like 200 bytes of data, or we can say 250 bytes to be safe on the side of data. And we have 200 million users. So 250 is the total size will be 250 byte into 200 million users. So if we break it down, 250 byte into 200 into 10 raised to power 6. So this will come out to be 10 raised to power 3 byte is 1 KB, 6 is 1 MB. So 25 into 250, 50 into 10 raised to power 3 into 1 MB, right? So 3 is equal to, it's equal to 50 GB. 50 GB, and then there will one more table will be friends list table, which will be simply user ID and friend ID, which is like 16 byte. And now here it will have, each user will have like, let's say 100 friends. So I'll say 200 million into 100. This will be the data. So again, 60 byte into million is equal to MB. So, and then 100 into 10, 10 to the raised to power 3 MB is 1 GB, and then 320 GB data. So overall data size is not a huge, but still it is pretty good. So 370 GB. But one thing I can easily see here, that the data is relational here. Both the tables we are talking here kind of like related to each other. So relational DB, we will go with it. So I'll say like, let's use SQL for it, or any other relational DB is also good, but I have just picked up the SQL here. So now there is one more thing, and I think we missed to talk about that in our functional requirement. That is that we want to store history, location history for 10 years. So now history data size. So what it will be, history will be, I think, the location history, which will be storing user ID, let, long, and timestamp, and this is 32 byte, and this is coming for at a time 20 million concurrent users. So for 20 million users in every 25 seconds. So I'll say 20 million divided by 25 seconds. This is per second data, which is equal to 32 divided by 25, somewhere coming around 1 point something. Let's simplify this, 1 byte into 20 billion, 20 million, sorry, not billion, and million will be 1 MB, so it is equal to 20 MB data per second. We say per day, so 20 MB into 24 into 60 into 60, which we simplify this by saying it is 10 raised to power 5, and this will come out to be 10 raised to power 3 MB is equal to 1 GB, and 10 raised to power 6 will be TB. So this is 2 terabyte of data per day. And if we want to store data for 10 years, then this will be huge DB, which is continuously growing DB. I'll say let's use the Cassandra DB here. That is the best supportive DB here, because this is continuously growing DB, and the cluster will also available with Cassandra, which is kind of like making it more reliable system and highly available system. So let's go with Cassandra. Now I think we have to, in this we have to deal with huge DB also, we have to deal with huge number of requests also. So we have pretty good understanding on the capacity math, guys. So now it's time to go to basic design. And I'm not talking about APIs here. We will talk more once we have the design about APIs. So let's start with the basic design. So in this case, we have a user one, and there is another user here, which is like a friend who will get notified. So let's call it friend one, and this will be a list of friends, 100 friends per user. So the user will send the location update to the let's call it nearby friend service. So the request will come to this, and this service will check in the database for the friends of this user here, which we said like it will be SQL database we're gonna use. So let's note down the responsibility of this service. One is fetch friends of the user. So now it has the 100 friends. Now it will check for the distance of each friend from this user. So this may be the for this it will store like maybe some cache here where it will store all friends locations. So it will check like, okay, for all these 100 friends, what are different their location, what is this user one location coming out, and who is like within 5 mile radius that need to be notified. So now what it will do, it will make a entry into historical DB, which is Cassandra, notify the friends in the given radius, which is 5 miles. So now friends know that this friend is within our 5 mile radius. So I just recorded here log history. So you see this notify friend service, like a request comes to this, gets all the user's entry from the SQL DB, and then it calculate the distance for each users, and then whosoever is within 5 mile radius, they get the notified here, and Cassandra DB is storing the DB. And then there is another application, and that will be manage friends. And the manage friend here, user can send like add, update, or delete the users, and that is updating the database. So now I think we have pretty good understanding at this point about the application, but one important thing which we missed here, notify the friend within 5 mile. How to notify the friend? Server on HTTP protocol, server cannot send message to any user. User will request something over HTTP, server will give the response for that request. So HTTP will not help us here. We need the WebSocket connection. Basically, each user is connected through a WebSocket connection to the service, and that is both-way connection. So let's talk about the functional requirement again and see what our service supporting here, what not. Our first requirement here is user should get notified if a friend is within 5 mile radius. So user will get notification here. The user should be able to add, update, remove friends. So we have managed friend service, which is doing all these things. So I think the functional requirements captured pretty well in this so far. Now let's see the non-functional requirement. The system should be highly scalable. See, fetching all the information for their friends from SQLDB, finding individual distance, logging in the history, sending it to friends, doing only one application, managing WebSocket connection is not a scalable approach. Definitely it's not scalable. Once the user count will keep increasing, the system will be like slow down, or it might get like dead also. All right, so to support non-functional requirements, let's deep dive into this design. So let me draw it here. So we have user and we have friends. So if you will see, we talked about in our design that we will be having the WebSocket connection. So to manage WebSocket connections, we know that we need a gateway layer here, and this will be gateway server cluster, and this will be managing what it will be doing. It will be managing WebSocket connections and auth, login and stuff, and it will be redirecting request. So now we have the WebSocket connection, and there will be session service, and there will be the session DB. Okay, so here is the session service gateway layer. Now if you will see closely here, what is happening, one user is publishing the location information and all the friends are receiving that information. So to handle this, we use the PubSub mechanism. So here we will use the same thing, PubSub, and what it will do, here will be a publisher, service, and this will publish the changes. This is PubSub server cluster, and here will be a subscriber which is sending back the information, receiving it from PubSub. Now subscriber publisher will add the location update into the user channel in the PubSub server cluster. So here will be a user one channel. All user will have their channel here, and the subscriber will be using the SQL DB here, and it will see who all different friends I need to subscribe for this particular user, and then it will subscribe for user one. And now user one, this location, the recent location update will come to the subscriber. So there will be one more caching layer here, maybe reddish. So this will be publisher will put information into the caching here. So this will be something like this: ID, user ID, and location. So the latest information will be in the reddish here for all the users. So subscriber will check for the friend's location from the caching, and it will calculate distance of each friend, and if it is within 5-mile radius, it will go to the friend. The notification will send to the friends. And because the session is out, these all services we have here are horizontally scalable. So this is Redis cache, and this is our PubSub server. Publisher will log the history also here, the Cassandra DB we talked about. All right, so let's see again here. Now user is sending request over the WebSockets connection through the gateway. Gateway is taking care of all WebSocket connections, because WebSocket maintain a live connection with user, so that gateway or like server can also send request back to, or like information back to the user. So now gateway will send the published information to the publisher service, and gateway is also a cluster of servers. Let me just mention it clearly here. So now we have publisher. Publisher is basically updating the cache here and publishing information into the cluster and making an entry in Cassandra DB. And now we have the information in the user channel. All the subscribed users in this channel will get the updates, and now the subscribing service get the update and look for the friend's location through the Redis cache and figure out how much distance from each friend it is, and if any friend comes within 5-mile radius, it notify to the user. Everything is horizontally scalable, and SQL DB we will may have copies of this to make sure the system is highly available. If one system goes down, others are there. We will have replicas for SQL DB. So I think we have pretty good. One more thing here, because the system is horizontally scalable, you guys might already be thinking about the load balancer. So this will be managed by load balancer. Now guys, one thing which we can deep dive a little more into is the PubSub server cluster. This is like, as we talked here, we have a lot of servers. So in case of Redis, as we decided to move on, we need 40 servers here. So in the PubSub, if you guys have already seen my consistent hashing video, then you can clearly imagine what is happening here. So let me explain it a little more here. and then I will put a link for my consistent hashing video so that you can get more insight. So how the PubSub cluster will work? So basically PubSub cluster will be a consistent hashing ring. On this ring we have slots for each hashed value, and then we allocate servers using the same hashing on this consistent hashing ring, something like this. We have the servers in place. These are the servers: server 1, server 2, and server 3 up to server 40. And keys in this space, if you imagine, like if we have key slot broken out from here, something like, these are the slots on this ring for each hash key value. So that's how the slots are here. So when a user ID comes here, it runs through this hashing algo, and now the hash value comes out for that user ID. Whatever hash value comes out, that particular slots get allocated for that user, and like this. So all this, like the circle I draw here, all the keys in this space will reside on or will be managed by server 1. All the keys in this space will be managed by server 2. Similarly, this space will be managed by server 3, and so on up to server 40. So that's how this works. Now there are virtual node concepts also, but I will put a consistent hashing video link in the description so that you can get more understanding of consistent hashing ring, how it works when a server is down and we move all the keys onto the next server in the clockwise pattern, how we uniformly distribute load among servers. So that video will give you more insight. But from this design point of view, you can see all the user IDs whose hash value is coming in this range are on server 1. And then one more thing we have here, and that is the zookeeper. Zookeeper responsibility is to manage this. So basically think like zookeeper is managing that S1 is holding these keys, S2 is holding these keys, and all those. So now when a request comes here for a particular user ID, if we go a little bit up onto design, so when a request for a particular user ID comes to this PubSub server, this run through the hashing algo and figure out what space it should be, and accordingly the request will go to that particular server. So if the user is on server 1, the channel of user is on server 1, it will be here. Subscriber will also use the same mechanism to subscribe the user channel on different servers. One more thing here is that these servers are stateless, but at the same time the server is storing information of subscribers. Basically, for a particular user ID, for example this particular ID, if there are subscriber ABC who subscribed for this particular user, once this server gets down, they need to be notified so that they can subscribe now to the new updated server who replaced this one. So that is something which kind of make it stateful, because this has to maintain a state that these are my users and these are the subscribers. So we need to be extra careful when we take a server down, that all the subscribers are notified that the server is down, and now the user information who you are interested in is on these servers, so they can subscribe back onto those servers. So I think guys, we talked about the PubSub, and PubSub we have discussed in detail. So and as I said, I will put the consistent hashing ring video that will give you clear understanding how this entire thing works. And then our service is horizontally scalable. Let's quickly run the non-functional requirements. So we have highly scalable system, yes. Highly available, yes. Consistent. So when a user comes in 5-mile radius, it may take up to 25 seconds, because the location is coming in 25 seconds. But once the information comes here, the system gives the or notify the user. So yes, this is consistent and low latency. We have the low latency in our system. And yeah, I think that looks like pretty reasonable design, guys. So thank you so much for joining the session, guys, and please don't forget to subscribe my channel, and see you in next session. Thank you.